Hello and welcome to the free CCNA CyberOps instructor training, brought to you by the Open University Cisco Academy Support Center and the Institute of Coding. It is the 18th of November 2019 and we're here at 8 o'clock UK time for Chapter 9, Cryptography and Public Key Infrastructure. Hello to everybody who's joining us for this session. Some people have actually managed to do the CCNA 2 session before this, and some probably the IT Essentials session before that as well. In which case, well done. It's a long day. It's the old Monday evening. Yeah. Okay, so we've got an interesting session ahead of us here. Chapter 9 already. Making very good progress through the course. Hello again to everybody. So, cryptography and public key infrastructure. We'll make a start. The first thing we need to think about is, what is cryptography? So we need to think about securing air communications. And information security, of course, is concerned with protecting network infrastructure devices and securing data as it travels on the network. Of course, the data is normally worth vastly more than the network infrastructure devices, but the network infrastructure devices are critically important to transport that data. Cryptography helps us realize what are known as the 4 objectives of information security. These are data confidentiality. In other words, only the authorized users should be able to read the data. This is normally provided by encryption. Data integrity. This means that the data has not been altered by any unauthorized parties, not tampered with, not corrupted. This is done using integrity checking, hashing algorithms and the like. Origin authentication. The data has actually originated at the expected source. And finally, non-repudiation. In other words, the integrity of the message is irrefutable by the sender. There's no way to turn around and say, no, that was not sent by that person, that message. Okay, so Cryptology. Cryptology consists of cryptography and cryptanalysis. Now, cryptology is the science of making and breaking secret codes. So these are two different disciplines. Cryptography, this is the development and use of codes that are used in communicating privately. Specifically, it is the practice and the study of techniques that are used in order to secure communications. And on the flip side, we have cryptanalysis. This is the breaking of those codes, specifically the practice and study of determining and exploiting weaknesses in cryptographic techniques. Now, this is an old subject. It goes back thousands of years. A cipher is an algorithm which consists of a series of well-defined steps that can be followed as a procedure when either encrypting or decrypting messages. There are many different types of ciphers. Go way back to the Romans, the Egyptians, probably the Babylonians and Sumerians before that. The following types of ciphers have been used over the years. We have what's known as the substitution cipher. The substitution cipher retains the letter frequency of the original message. So in other words, with a substitution cipher, we literally substitute one letter for another on a single operation. So if you're talking about the English language, for instance, the letter E is the most common letter in the English language, followed by T. If you actually have enough data in the message, enough actual information, you can do a frequency analysis, and if you find out that the letter J, for instance, is more frequent than any other letter, there's a very good chance that the letter J has been transposed, or substituted I should say, with the letter E. In a transposition cipher, no letters are actually replaced, they're just simply rearranged. And what we've also got is we've got what's called a polyalphabetic cipher. And a polyalphabetic cipher, these are based on substitution using multiple substitution alphabets. One of the most interesting to most people ciphers is the one that was developed before the Second World War, which was widely used by the German military, which of course is the famous Enigma machine. And if you want to have a little play with your students with an Enigma machine, something that I found on the internet many years ago, I'll just very quickly show you, is an online Enigma machine. Now bear in mind, this is a shockwave flash file, so it won't play in Chrome, but providing you tell it to, Firefox will play it fine. And you can get a hold of this simply by typing in Enigma machine into Google, go into the Wikipedia page, and down in the resources link there are 3 different types of Enigma simulator, and it's basically the middle one. But this is rather nice, and I've used this with my students before, and what you can see here is you can actually see these letters down the bottom here. These represent the plug board, which is at the front of the Enigma machine, where you could plug different wires in different sequences. We have the rotors, which have different internal wiring on each rotor. You can actually swap the rotors around as well, put different rotors in different places. This is simulating a 3-rotor Enigma. These rotors in the real thing were simply plastic, a Baker-like plastic with internal wiring inside and pins on the outside. 26 positions, randomly wired to 26 other positions depending on which rotor it is. So you've got different rotors to choose from. You've got different positions to put the rotors. You can actually move those around. The signal, when you press the key, goes up the wire, through the rotors, hits the reflector rotor, and then comes back again. So it actually goes through 7 steps, and every time you hit a key, the rotor is increased by 1. So, for instance, I could type "Hello World." You'll notice it doesn't accept spaces, because spaces are a dead giveaway in a code. You can tell the amount of letters in each word if you start putting spaces in. So it will simply ignore any spaces that you type. But you'll notice every single time you type a letter, the rotor starts to move around, and this gives you your output. And it's quite nice actually to get students working on this. They can't break it. But it took a phenomenal amount of effort to break this. But what they can do is they can set the rotors up and the positionings and things like that, and they can actually create codes and send them to each other, and providing that they put the rotors in the correct positions, they can decode them. But of course, during the Second World War, phenomenal effort was put into cracking these machines. The amount of combinations is absolutely staggering, and the world's first computers were actually full-blown digital electronic computers were actually developed to crack these codes, which is an interesting thing. For instance, like the Colossus. Okay, so the history of ciphers and codes goes back a very long time, long before the Second World War, the First World War, right back to the times of the Romans, the Egyptians, the Babylonians, and the Sumerians. Cryptanalysis, or code breaking. There are many different types of cryptanalysis or code breaking methods, such as brute force, ciphertext, known plain text, for instance. Brute force. In the case of brute force, the cryptanalysis tries every single possible key combination, knowing that eventually one of them will work. In fact, there is no defense against brute force, in so much as eventually, given enough time, it will always find the answer. However, the key thing is to make the amount of time that's required to find that answer so uneconomical that there's no point even trying. Now, if you've got a situation where, for instance, you've got a router that is secured with a username and a password, for instance, what you would do is you could actually create a login block on that router where it would only allow you 3 goes at typing in the correct password, and then it would block any further goes for perhaps 2 minutes. This would stop brute force or dictionary attacks or things like that, purely because the computers are capable of sending thousands and thousands, or hundreds of thousands in some cases, of guesses of passwords a second at the system. But obviously, if every time you get 3 of them wrong, it stops for 2 minutes, then that basically stops that from being an economical way of doing things. So ciphertext, the cryptanalysis has ciphertext of several encrypted messages, but no knowledge of the underlying plain text. We've got known plain text, where the cryptanalysis has access to the ciphertext of several messages, but knows something about the plain text that was ciphered. This gives them a bit of a clue. Chosen plain text, so where the cryptanalysis chooses which data the encryption device encrypts and observes the ciphertext output. Chosen ciphertext, where the cryptanalysis can choose different ciphertext to be decrypted and has access to the decrypted plain text. So you can start a kind of reverse engineering there. And man in the middle, where the cryptanalysis knows a portion of the plain text and the corresponding portion of the ciphertext. And in fact, that was one of the things that helped the code breakers at Bletchley Park decipher the Enigma machine coding. Was that one particular German weather station would always, the very first thing that they would type would be Heil Hitler. Because it was always the very first thing that they typed, they could actually reverse engineer the coding on that one. So, keys. So with modern technology, the security of encryption lies with the secrecy of the keys, not of the algorithm. Okay, so the algorithms are generally publicly known. So for instance, data encryption standard DES, triple DES, the advanced encryption standard, these are all publicly known algorithms. However, the secrecy doesn't lie in the algorithm, it lies in the keys. And the bigger the key, the more chance you have of keeping it very, very secret. So the two terms to use when describing keys are: 1, the key length. This is also known as the key size. This is measured in bits. And also the key space, which is the number of possibilities that can be generated with a specific key length. So as the key length increases, the key space will increase exponentially. And we can also actually have a little look at that as well, because obviously what we're using here is we're using binary. So if we get a calculator out, we can simply put in 2 raised to the power of 56, for instance, which will give us a key space of a significant key space. I'm not sure what you would pronounce that number. That's 72,000 million approximately. That's 2 raised to the power of 56. However, every time we add an additional bit, we double the key space. Now, this is something that a lot of students can't quite figure out initially. You'll normally say to them something like, for instance, if I've got a 64-bit algorithm and I upgrade it to a 128-bit algorithm, how much stronger is it? And it's amazing how many say, well, hold on, 128 is twice the size of 64, so it's twice as strong. Of course, it's not twice as strong, it's massively more strong than that. If we go from a 56-bit key space to a 57-bit key space, we literally double the number of combinations. If we go to a 58-bit key space, we double the number of combinations again. So you can see there is a significant difference. Okay, if we go on to look at integrity and authenticity, we can make use of what's known as cryptographic hash functions. And a cryptographic hash this is used to verify and ensure data integrity. The hashing itself is based on a one-way mathematical function, so it's relatively easy to compute, but is significantly harder, to say the least, very significantly harder to reverse. So a cryptographic hashing function can also be used in order to verify authenticity. The hash function will take a variable block of binary data, which is known as a message, and it will produce a fixed length condensed representation called a hash. This is quite clever. So even though the block of binary data on the input is variable or arbitrary in length, it will always produce a fixed length hash. This resulting hash is sometimes known as either a message digest, or a digital fingerprint. Now with a hash function, it is computationally infeasible, not impossible, but infeasible, for two different sets of data to come up with the same hash output. So you can be pretty sure that if you, for instance, download an operating system, and on the operating system page they say that there's a message digest 5, or possibly a SHA-256 hash for that operating system, then if you download it and you run on your local machine once it's downloaded, MD5 or SHA hashing, and you produce exactly the same hash that's on the website, you can be pretty much guaranteed that there has been no tampering, alteration with the operating system as you were downloading it. So this is widely used when downloading software, for instance. If you've ever downloaded a Linux ISO image, you'll notice that you'll have MD5 or SHA-256 hashes. You should always download the hash and then run the hash function to check to make sure that the output is correct and it matches. In fact, I can just quickly show you that. I think if we let's have a little look. Right, let's lose the calculator for a moment. In fact, the quickest way of doing this wouldn't be to open up a terminal window, it would be to open up the file manager. Let's just see if I can find some downloaded ISO images very quickly. Backups. Where have I got some ISO images? Documents. I must have some ISO images on here somewhere. Oh, ISO images, there we go. Huge folder with ISO images written on it. Okay, so for instance, if we look at this Kali Linux ISO image, for instance, what we can do is, now I don't know actually whether that's an MD5 sum that we're going to use or a SHA-1, but from the Linux command line you can literally, well, we've got two Kali Linuxes there, so we'll go for the ISO image. You can literally run MD5 sum followed by the name of the ISO image, and what it will do is it will generate the MD5 sum. It'll take a little while to do it because it's computationally relatively intensive to do this, and then you can compare that generated MD5 sum or digest with the one that's on the website, and that way you can guarantee that the information has come over completely unaltered and untampered with and uncorrupted. Likewise, there's such a hash as a SHA-256 hash, SHA-256 sum. You can do this from PowerShell in Windows as well. So if there isn't an MD5 hash, there will almost certainly be a SHA-256 hash. And like I say, we're kind of spoiled on Linux systems because you can do this directly from the command line. Notice how much bigger the SHA-256 hash is. Now the chances of two different data files, or operating systems in this case, having exactly the same hash is not impossible, but incredibly rare. Mathematically infeasible, as they say. Every time the data is changed, so every time the data is actually changed, the hash value will also change. Okay, so with a cryptographic hash operation, mathematically this is little h equals big H times x. the cryptographic hash function should have the following properties, where the input can be any length, whilst the output is a fixed length. H times x is relatively easy to compute for any given x, so one direction it's nice and easy. However, it is a one-way and not reversible. And it's also known as collision-free. And what we mean by collision-free is that two different input values will result with different hash values. Okay, so typical hash functions used to determine the integrity of a message. In my case, I actually determine the integrity of a ISO image, which would be used to create a bootable CD for installing an operating system. But of course, it works the same way for a message. Are the MD5 and the secure hashing algorithm. They ensure that the data has not been changed accidentally or intentionally. So we've got MD5, SHA-1 and SHA-2. I didn't do SHA-1 and SHA-2, I did the SHA-256, which is of course a 256-bit hash. The MD5 uses a 128-bit digest. So this is a one-way function that produces a 128-bit hashed message. MD5 is now considered to be a legacy algorithm, so it's recommended that you use a SHA or SHA, secure hashing algorithm. SHA-1, very similar to MD5, is a 160-bit hashed message. Also known to have flaws, SHA-1. SHA-2, next generation algorithm, should be used whenever possible. And of course SHA-256 is a version. So while hashing can be used to detect accidental changes, it cannot be used to guard against deliberate changes. So there is no unique identifying information from the sender in the hashing procedure. So if we have a deliberate change, and the sender changes the hash, then you're not going to be able to work out what the problem was there. So, in order to add authenticity to integrity assurance, in other words, to give us that facility, we make use of what's known as a keyed hash message, or keyed hash message authentication code, or HMAC. Okay, so adding authentication, the HMAC will make use of an additional secret key as an input to the hash function. So not only do we have our data of arbitrary length, but we also have a secret key goes into the hash function. Only the sender and receiver know the secret key, and the output of the hash function will now of course depend on not just the input data but also the secret key. So therefore the only parties who have access to the secret key and then can compute the digest of the HMAC function. So if the digest that is calculated by the receiving device is equal to the digest that was sent, then the message has not been altered. Encryption. Encryption allows us to have confidentiality. There are two different classes of encryption, and they differ in how they use their keys. We have symmetric encryption algorithms. So these encryption algorithms use the same key to encrypt the data as to decrypt the data. And these are based on the premise that the communicating party knows the pre-shared key. The big weakness there, of course, as you can think, is how do we share those keys safely? And we have the asymmetric encryption algorithm. This encryption algorithm uses different keys to encrypt and decrypt the data. And these are based on the assumption that the two communicating parties have not previously shared a secret. And they must establish a secure method of doing so. Now, asymmetric algorithms are very resource intensive and are slower to execute. Asymmetric algorithms normally revolve around some very, very clever mathematics. So they make use of prime numbers, modulo mathematics, so-called clock mathematics, Euler's little theorem. There's some very heavy mathematics in there. basically with an asymmetric algorithm you create two keys. You create what's known as a public key and a private key. Those two keys are mathematically linked to each other, so any data that is encrypted by the public key can only be decrypted by its associated private key, and vice versa. So if we look at the slide, symmetric encryption algorithms, they use the same key to encrypt and decrypt. The key lengths are relatively short, between 40 bits and 256 bits on average. They are much faster than asymmetric encryption, and they are commonly used for encrypting bulk data, such as the data that's transferred by a VPN. Asymmetric encryption will use two different keys, one to encrypt, one to decrypt. So we've got our public key and our private key. The key lengths are much longer, generally between 512 bits and 4096 bits. They are computationally much more intensive, so they are much slower than symmetric encryption, and they are commonly used for quick data transactions. They are also used, of course, for key exchange, so we can exchange keys making use of asymmetric algorithms, and then once the keys are securely exchanged, we can switch over to a symmetric algorithm for bulk data transfer. Okay, so to recap, symmetric algorithms use the same pre-shared key in order to encrypt and decrypt data. Nowadays, symmetric encryption algorithms are very widely used with VPN traffic. Typical example would be AES, the Advanced Encryption Standard. This is because symmetric algorithms are much less CPU intensive than asymmetric encryption algorithms. So when we're using a symmetric encryption algorithm, like any other type of encryption, the longer the key, the longer time it will take for somebody to discover the keys. So most encryption keys for symmetric encryption algorithms are between 112 and 256 bits. Now, symmetric encryption algorithms, to go a little further, they are often classified as either block cipher or stream cipher. Block ciphers transfer fixed length blocks of plain text into common blocks of ciphertext, 64 or 128 bits. Stream ciphers, they will encrypt the plain text 1 bit at a time. So again, taking a typical example, widely used in virtual private networks is AES, the Advanced Encryption Standard. This is a block cipher. It's a symmetric encryption block cipher, AES. Whilst the reverse ciphers, the RCs, are stream ciphers. Asymmetric encryption algorithms, also known as public key algorithms, these are designed so that the key that is used for encryption is different from the key that is used for decryption. The decryption key cannot, in any reasonable amount of time, be calculated from the encryption key and vice versa. The mathematics is absolutely incredible in the way that these work. Asymmetric algorithms use a public key and a private key. Both keys are capable of the encryption process, but only the complementary paired key is required for the decryption process. The process is also reversible, so data encrypted with the public key requires the private key to decrypt and vice versa. The process that enables symmetric key algorithms to achieve this process then enables asymmetric encryption algorithms to achieve confidentiality, authentication, and integrity. So, let's have a little look at this encryption, this asymmetric encryption. Asymmetric encryption algorithms are used to provide confidentiality without pre-sharing the password. So the confidentiality objective is initiated when the encryption process is started with the public key. So summarizing the process, the public key encrypts plus the private key decrypts. which gives us the confidentiality. So when the public key is used to encrypt data, the private key must be used to decrypt data, and the private key is kept private. Okay, the authenticity objective is initiated with the private key encryption process. So this is the private key is used to encrypt, and the public key is used to decrypt. So when the private key is used to encrypt the data, the corresponding public key must then be used to decrypt the data, and because only one host has the private key, only that host could have encrypted the message in the first place, providing the authenticity of the sender. So when a host successfully decrypts a message using the public key, it is trusted that the private key encrypted the message, which therefore verifies the sender. So not only can we take use of confidentiality, where the message is encrypted with the public key, but we can also take care of authentication where the message is encrypted with the private key. So it basically serves both tasks. If we combine the two processes together, this allows us to provide confidentiality, authentication, and integrity. So we've got Bob's public key plus the plain text gives us our encrypted text. We take the hash, we combine that with Alice's private key, which gives us our encrypted hash. This is sent across. The encrypted hash can then be decrypted into the straightforward hash with Alice's public key, and then that is then turned into plain text by Bob's private key. Notice that the private keys have never left their individual systems, and yet we've managed to have confidentiality via the encryption and authenticity via the hashing. Confidentiality and authenticity by the private public key system, and integrity via the hashing. Okay, Diffie-Hellman. Diffie-Hellman is widely used by protocols such as SSH, the secure shell. Sorry about this, my mouse has absolutely disappeared again. Okay, got it. Diffie-Hellman is an asymmetric mathematical algorithm, and it allows two computers to generate identical shared secrets without having communicated beforehand. So the new shared key is never actually exchanged between the sender and the receiver. However, because both parties know it, the key can be used by an encryption algorithm in order to encrypt traffic between the two systems. So, typical examples where Diffie-Hellman is commonly used would be where data is exchanged using an IPsec VPN, or where data is encrypted on the internet using either SSL, Secure Sockets Layer, or TLS, Transport Layer Security, or SSH data is being exchanged. If you have a little look at the diagram here, what we've got Alice and Bob. In order to illustrate how this works, the Diffie-Hellman key exchange process begins with Alice and Bob agreeing on an arbitrary common color that does not need to be kept secret. So they've both agreed on yellow in this example. Next, both Alice and Bob will select a secret color. In this case, Alice chooses red, whilst Bob chooses blue. These secret colours will never be shared with anyone. The secret colour represents the chosen private key from each party. Alice and Bob now mix the shared common colour, yellow, with their respective secret colours in order to produce a private colour. Therefore, Alice will mix yellow with red in order to produce orange, whilst Bob will mix yellow with blue in order to produce his private colour of green. Alice now sends her private colour, orange, to Bob, and Bob sends his, green, back to Alice. Alice and Bob next mix the colour they received with their own original secret colour. So that would be red for Alice and blue for Bob. And the result is a final brown colour mix which is identical to their partner's final colour mix. In other words, the final key is identical to their partner's key. So they've managed to get a key across without ever exchanging the actual key. So the brown colour represents the resulting shared secret key between Alice and Bob. Now, this is a simplistic way of looking at it, but in reality the security of Diffie-Hellman is based on the fact that it uses incredibly big numbers in its calculations. So for example, if we have a Diffie-Hellman 1024-bit number, this is roughly equal to a decimal number of 309 digits. Now I couldn't even do that on my calculator, I don't think. I think that's going to completely, well, it's bound to break the calculator, but just for a bit of fun. If you want a rather nice little calculator to use in Linux, there's a calculator called Qcalate, which is the one I was using earlier. Something tells me that this is going to drop into scientific mode on a massive scale here, but if we take this calculator and we put in 2 raised to the power of 1024, that's incredible. It didn't drop into scientific mode. I tell you for why, because I actually told it not to. I can remember setting up the settings on this saying do not use scientific mode. This calculator is absolutely remarkable. The number is so big, in fact it goes right across the board there. However, the neat thing with this is if you hover over the number, you can actually see it word wrapped. So that is what a 1024-bit key works out at. Whoa. Incredible. Okay, so if we consider that a 1024-bit Diffie-Hellman key is roughly equal to a decimal number of 309 digits, there's 309 digits there, and considering that a billion is only 10 decimal digits, you can easily imagine the complexity of working with not just one but multiple 309-digit numbers. However, there is a downside. Unfortunately, asymmetric key systems are extremely slow for any type of bulk encryption. So this is why it's common to encrypt the bulk of traffic using a symmetric algorithm such as triple DES or AES, and then use the Diffie-Hellman algorithm in order to create the keys that will then be used by that encryption algorithm. Wow. Digital signatures. So a digital signature is a mathematical technique which is used in order to provide 3 basic security services. These are known as code signing, digital certificates, my fault. In order to provide authentication, integrity and non-repudiation in the form of code signing and digital certificates. So code signing, this is used when data integrity for data integrity and authentication purposes. So code signing is used to verify the integrity of executable files that are downloaded from a vendor's website, for instance. It also uses a signed digital certificate to authenticate and verify the integrity of the site. And a digital certificate, these are similar to a virtual ID card, and they are used to authenticate the identity of a system with a vendor website and establish an encrypted connection to exchange confidential data. Okay, we have 3 digital signature standards algorithms that are used for generating and verifying digital signatures. We have the digital signature algorithm, or DSA. This is the original standard for generating public and private key pairs and for generating and verifying digital signatures. We have what's known as the Revist, Shamir and Alderman algorithm. They were researchers at the Massachusetts Institute of Technology. RSA is an asymmetric algorithm that is commonly used for generating and verifying digital signatures. And we have the elliptic curve digital signature algorithm. And this is a new variant of the digital signature algorithm that provides digital signature authentication and also non-repudiation, with the added benefit of computational efficiency, small signature size and minimal bandwidth. Okay, so digital signatures are commonly used to provide assurance of authenticity and integrity of software code. For instance, executable files wrapped in digital signed envelope, which allows the end user to verify the signature before they take the risk of actually installing the software. Digitally signing code provides the assurance about the code, that the code is authentic and it's actually sourced from the publisher, that the code has not been modified since it left the software publisher, and that the publisher undeniably published the code. This provides non-repudiation. Okay, so looking at a typical digital signature, we've got an issued to field, a certificate authority field, and an expiry date field. The digital signature enables users, hosts, and organizations to securely exchange information over the internet. So specifically, it is used to authenticate and verify that the users sending a message are who they claim to be. In other words, digital signatures can also be used to provide confidentiality for the receiver by means, which means that they can encrypt a reply. Whew. Okay, so moving to public key management now. So when establishing a asymmetric connection between 2 hosts, the hosts will exchange their public key information. What we have is we have trusted third parties on the internet that validate the authenticity of these public keys using digital signatures. The third party issues the credentials, which are difficult to forge. So from that point forward, all individuals who trust the third party, they can simply accept the credentials that that third party issues. So public key infrastructure is an example of a trusted third party system, referred to as a certificate authority. So the certificate authority issues digital signatures that authenticate the identity of organizations and users. And these signatures, these certificates I should say, are used to sign messages and ensure that the messages have not been tampered with. So, public key infrastructure is therefore needed to support large-scale distribution and identification of public encrypted keys. It facilitates a highly scalable trust relationship, and it consists of hardware, software, people, policies and procedures needed to create, manage, store, distribute and revoke digital signatures. So not all PKI certificates are directly received from a certificate authority, but a registration authority is a subordinate to a certificate authority and is certified by the root certificate authority to issue certificates for specific uses. Okay, so many vendors will provide CA servers as a managed service or as an end user product. Now, the organizations may implement private public key infrastructures, making use of Microsoft Server or OpenSSL. Certificate authorities will issue certificates based on classes, which determine how trusted the certificate is. And the class number is determined by how rigorous the process was that verified the identity of the holder when the certificate was first issued. The higher the class number, the more trusted the certificate. So some CAs, or certificate authorities, public keys are preloaded, such as those that are listed in web browsers. In addition to that, an enterprise can also implement public key infrastructure for internal use. So we have the classes, which are identified in the table. We also have the PKI trust system. So PKIs can form different topologies of trust. The simplest is the single root PKI. Okay. On a larger network, however, the PKI certificate authorities may be linked into two basic architectures. So we've got a cross-certified certificate authority topology. So this is a peer-to-peer model in which the individual CAs will establish trust relationships with other CAs by cross-certifying the certificate authority certificates. Then we have the hierarchical certificate authority topology, where the highest level CA is called the root CA, and it can issue certificates to end users and to subordinate CAs. Now, we need to make sure that we have interoperability between public key infrastructures and supporting services. This is a concern because many CA vendors have proposed and implemented proprietary solutions instead of waiting for the standards to develop. Okay, so in order to address the interoperability concern, the IETF, the Internet Engineering Task Force, published the Internet X509 PKI certificate policy and certificate practices framework. This is specified in Request for Comment 2527. So the X509 version 3 standard defines the format of digital certificates. Okay, certificate enrollment, authentication and revocation. So all systems that make use of or leverage the public key infrastructure must have the CA's public key, known as the self-signed certificate. The CA's public key verifies all the certificates issued by the CA and is vital for proper operation of the public key infrastructure. The certificate enrollment process will begin when CA certificates are retrieved in band over the network, and the authentication is done out of band using a telephone. The system enrolling with the PKI contacts the certificate authority to request and obtain a digital identity certificate for itself and to get the CA's self-signed certificates. And the final stage verifies that the CA certificate was authentic, and this is performed using an out-of-band method such as plain old telephone system to obtain the fingerprint of a valid CA identity certificate. Now, a digital certificate can be revoked if the key is compromised or it's no longer needed. So some of the applications of the public key infrastructures are secure sockets layer, transport layer security, certificate-based peer authentication, secure network traffic using IPsec VPNs, HTTPS web traffic, controlling access to the network using 802.1x authentication, securing email using SMIME, secure instant messaging, approving and authorize applications using code signing, protecting user data using the EFS, the encrypted file system, or implementing two-factor authentication via use of smart cards or securing USB devices. Okay, also regarding encrypting network transactions, so threat actors can use SSL or TLS to introduce regulatory compliance violations, viruses, malware, data loss or intrusion attempts on a network. Other issues may be associated with validating the certificate of a web browser. So when this occurs, the web browser will display a security warning You can see the little old security warnings popping up on the web browsers. We've got a situation where we have the validity date range. So with our X509v3 certificates, specify not before or not after dates. This is an important thing when you're actually setting up a CA server. You've got to be very, very careful with the time. Should be synchronized using network time protocol to make sure that the time when everything is in step and very close. Signature validation error. If the browser cannot validate the signature on the certificate, then there is no assurance that the public key in the certificate was authentic. Okay, last slide, ladies and gentlemen. Boy, that was a heavy chapter, especially on the third video of the night. Network monitoring becomes more challenging when packets are encrypted. Oh yes. So because Hypertext Transfer Protocol Secure introduces end-to-end encryption of HTTP traffic via transport layer security or secure sockets layer, it's not easy to peek into that user traffic. So some of the things that a security analyst could do is configure rules to distinguish between SSL and non-SSL traffic, HTTPS and non-HTTPS SSL traffic. They can enhance security through server certificate validation using CRLs and OCSPs. They can implement anti-malware protection and URL filtering of HTTPS content, and of course they can deploy the Cisco SSL appliance to decrypt SSL traffic and then forward it on to intrusion prevention system appliances to identify any risks that are normally hidden by SSL. Ooh, okay, wow, that was a rather huge amount of information there. Chapter 9, done, dusted. I've tried to cover as much as I could within the time that was available. It's definitely a chapter that you will need to read through very, very carefully. It is a very interesting chapter, much more interesting than I could have possibly made it with a rather dry and technical presentation. But it's definitely one of the more interesting subjects, cryptography and cryptology, well, cryptology, so in general. Next week we're back for chapter 10 when we look at endpoint security and analysis. So that will be on the 25th of November at same time. I hope you found that useful, and best wishes to everybody. Oh, I'm going to now go and have myself a nice cold pint of Guinness, I think.